and we're going to be looking at the compositions of functions. I'm going to start you thinking about this in the mind's on. First of all, I want you to understand what a composition of functions is. The idea is that you input a value from another function. In this case, f at x has an input from the output of g at x. This is why the g at x is written inside of the bracket for f at x, because it provides the input into f at x. There are other notations for this. In this case, we say f of g at x, which means the same idea. And sometimes they write them without the x in there, or there may not even be brackets, and it would just say f of g, which again means f of g at x. Writing this out to represent what's actually happening, an x input goes into g at x, and then the output y of g at x goes into f at x, and then the ultimate output of the function, it comes out of f at x. So what we see here is the connecting in the middle, that the output y of g at x is the input x to f at x. Now, to get you thinking about this process, what I'd like you to do is two things. One would be to stop the video, and in these two functions here, where g at x is the input to f at x, to find where these connect. Because when you do these functions, a similar process to when we had to have overlapping domains when we were doing other operations with functions, in this case, the output of the input function, so the output of g at x, has to connect with the input values of f at x. For example, here, this output is 3, and this input is 3, so those connect together. So what I want you to do is find the ones that connect together and just draw a line to them. So if I were to continue with this 8 connects with this 8 input here. Looking at this 7 and this 2, there are no 2 inputs or 2 x values here. So this does not connect with the other function. There is a -5. So this -5 here would connect with the input to this point here of this function. 4 is not represented in any x's, so that does not connect. And then finally, 20 and then 9, the 9 connects to this last point here, which is an input of 9. Now what I'd like you to do to continue thinking about this is to go ahead and write out these values individually, keeping in mind that these middle values in the middle, the output from g at x and the input to f at x would have to be the same value. And again, I'm just trying to get you familiar with how these work in terms of connecting together where one function is an input to another. So I would suggest you go try filling this table in on your own as well. Filling this in, looking at our first point there, the input is 0, the output of g at x is 3. Then coming over to f at x, its input is 3, and its output is 10. So in terms of this function here, f of g at x, when we put 0 into this function, the ultimate output is 10. Looking at the input 4, the output is 8, and that results in an input to the f at x of 8, and its output from there is 4. Looking at the next one, 9 is the input. The output is -5. That connects with this point where its input is -5 for f at x, and the output is 9. Finally, looking at the input 20, its output is 9, and that connects to this input in f at x of 9, and the output is 14. Now, using this table and this idea then, we're going to go and use the same scenario that we have here, but use the notation as it's intended. And now that we've seen it in this long form, see if we can't connect that to doing it in terms of the algebraic method of representing it. And one thing I want you to note here is note the inputs here and where they come from. Later on, there's a question that relates to this. And note the outputs and where they come from. Coming down here to the notation, we're supposed to find f at g at 0. F at g at 0. So once again, I'm going to take a moment and break this down. G at 0, and we have it in our table now. G at 0 is 3. So in this notation here, the G at 0, its output is 3. Now we're using the input of 3 into F. And where 3 is an input for F, the output is 10. So the answer to this is 10. So F at G at 0 is equal to 10. Looking at F at G at 9, first of all, starting with G at 9, G at 9, its output is minus 5. So that equals minus 5. What we now have is F at minus 5. And for the F function, when its input is minus 5, its output is 9. So the answer to this is 9. So F at G at 9 is equal to 9. So here I have the question, what are the domain and the range of f at g at x? So again, we have it in this table here. First of all, ultimately, this is the input to this whole function f at g at x. Its input is right here. So this is the domain for this function. And then ultimately, the output for f at g at x is over at this end. So this is the range. The domain is a finite set. So we just have to list the values. The domain is 0, 4, 9, and 20. The range is equal to, looking at the right-hand side, 4, 9, 10, and 14. And down here we see the question, how do the domain and range relate to the original functions? Well, hopefully what you've noticed is the domain comes from this initial function, which is the starting of it all, because its input is what starts this working. And then ultimately, the output, which is the range, comes from f at x. The domain comes from the inner function, which is the input, and the range comes from the outer function. Now we're going to look at this idea algebraically. Looking at example number 2, we have two functions, f at x equals 2x cubed minus 3x squared, and g at x equals 3x plus 2. In A, we're asked to find algebraically what f at g at x is. This step I'm going to put in here, you don't have to do, but I find that it can help people to think about what's happening. So this notation doesn't seem as clear of what's happening as when we put these brackets and put g at x in here. And this is very clear that g at x is the input. And so g at x is 3x plus 2. So what we have is f at 3x plus 2. This is our input. This expression now is going to be replaced with x in this function here. That leaves us with 2, 3x plus 2 cubed minus 3, 3x plus 2 squared. Now we need to do our algebra here. If anybody knows how to do now we need to do our algebra here. First of all, we need to multiply a binomial times a binomial. So these are 3 of these expressions multiplied together. I'm going to expand that out so it's clear what's happening. And then I'm going to leave this for the moment because we're going to be doing that operation here already, so we can use that work over here. So we have 2, 3x plus 2. 3x times 3x is 9x squared. And now I'm going to save a step and do my combining of like terms in the middle as I go. 3x times 2 is 6x, and then 2 times 3x is 6x. So that's 6x plus 6x, which is 12x in the middle. And then 2 times 2 is 4. And this is where I save myself some time because this is the exact same answer over here. Continuing on, we have 2, and then I'm going to multiply the 3x times each of these terms. 27x cubed plus 36x squared plus 12x. Then with the 2, plus 18x squared plus 24x plus 8 minus 27x squared minus 36x minus 12. And I need brackets around these first set here up to the 8 because those are all doubled or multiplied by 2. Now you can see here that I didn't leave enough room below, so I will have to come up here and continue. Two times 27x cubed is 54x cubed. Plus 72x squared. Plus 24x. plus 36x squared plus 48x plus 16 minus 27x squared minus 36x minus 12. Finally, simplifying any like terms, we have 54x cubed. Looking at the x squareds, we have 72 plus 36, that's 108, minus 27, that's 81x squared. Looking at the x's, we have 24x plus 48x, which is 72x, minus 36x, which leaves us with 36x. And finally, the numbers, we have a 16 minus 12, which leaves us with plus 4. Looking at the domain, we see that this function is a cubic function. And we know that with cubic functions, the domain is x element of R. Domain equals the set of x is an element of R. Now what we're asked to do is find 2 points on the function. The input value for this question here is 3. So what we want to do is simply take 3 and put it into this resulting function. So this equals 54 times 3 cubed plus 81 times 3 squared plus 36 times 3 plus 4. This works out to 2,299. Doing the same for the input value of minus 2. 54 times minus 2 cubed plus 81 times minus 2 squared plus 36 times minus 2 plus 4. And this works out to minus 176. The last step in this question is we'll go ahead and graph the function so that we get an idea of what it looks like. Already it's a cubic, so we have a sense from this of what it should look like. It has a positive leading coefficient. We know that with a cubic, its ends go in opposite direction. In this case, because it's positive leading coefficient, if we put a negative in, we will get a negative out. So in the negative values, we will have the end going down to infinity. And then with the positive values, we will have the end going up to infinity. So this function will go from the third quadrant up and through to the first quadrant. Going over to Desmos. The function was y equals 54x cubed plus 81x squared plus 36x plus 4. And there's our function. I'm just going to change the scale on this a little bit. Let's go from minus 5 to 5. And there, that's a good view of that graph. And I'll copy it and put it into the document. Putting our graph in. There's something I would like you to consider now that we have this graph in here. And that's just to think about the connection between these two functions. Remember, we talked earlier when we were looking at set notation and being able to analyze the points themselves, that the output of the innermost function, in this case g at x, its output is the input to this function. So let's take a moment and just consider the connection here. This is linear, and we know with a linear that the range of a linear function is y element of r. The domain of a cubic function is x element of r. So we see that the range or output of this function, as it relates to the domain or the input of this function, overlap entirely because they're both element of r. So there was no restriction here in terms of what values that we were working with. Now we will go and look at one more example. In example number 3, we are working with a quadratic and a square root function. I would encourage you to go ahead and go through this whole process on your own and then check back and see how you did. Completing this algebraically, once again we have f at g at x, and this time I'm not going to write the other notation. I'm simply going to take g at x and input it into f at x. So we have 3, and there's an x squared, so in place of the x, I'm putting the square root of x minus 2, which is g at x. And then I have a plus 2 out here. Simplifying, this one's much easier than the previous question. When we square a square root, we end up with what's underneath the root sign left. So what we're left with here is x minus 2, and then we have a plus 2. Simplifying that further, we have 3x minus 6 plus 2, which equals 3x minus 4, and that's simply a linear function that we're left with after this operation. Now, considering the domain, this question illustrates the need to go back to the original functions and consider them carefully. Even though this is a linear function, and so we might think its domain is x element of r, remember that it's a result of these two functions put together where g at x is the input. And remember that g at x is where the domain comes from, and this does have a restriction. Once again, this is our square root function. It must be greater than negative values underneath the root sign, so x minus 2 must be greater than or equal to 0. Solving for x must be greater than or equal to 2. That is the limiting factor for our domain. And then looking at the connection between these two, keep in mind that for this function, the result for y, because the answer to 2 minus 2 is 0, which is the lowest value of x possible, y, which is the way we planned it, is a value that's 0 or greater, because the answer to this has to be either 0 or a positive value. Y is greater than or equal to 0. This still works with this function because all of these values are contained with the inputs of this quadratic, where its domain is x's element of r. So all of these values of y, the output of this being numbers that are 0 or greater, all fit into this input value where its domain is x element of r, which is every number. So the connections between these two are fine, but we have to keep in mind that this is the domain for the whole function. So the domain here is equal to the set of x is an element of r such that x is greater than or equal to 2. Coming down to this value here, first of all, we're going to have to make sure and check that the input values we've been given fit the domain. So in this case, 3 is greater than or equal to 2. Subbing 3 in, we have 3 times 3 minus 4, which equals 9 minus 4, which is 5. Coming over to this function, we see that minus 2 is not in the domain. Therefore, there is no answer to this. What we will do is simply use a null set. There is no solution because minus 2 is not a valid input for this function. So the last step will be to graph this. And graphing a linear is very straightforward to us. We're still going to use Desmos, but keep in mind that we're going to have to keep this domain satisfied when we graph this. Coming over to Desmos, the equation is y equals 3x minus 2. And so in Desmos, we need to tell it what the domain of this function is. So we will use the brackets that we use for domain, and we will state that x is greater than or equal to 2. And then if we just adjust this graph, we can see that now it graphs this line, but with the lower limit based on the domain. And now I'll insert that into my document. And so there we have our graph, and now you can go ahead and work on the practice for this topic.